So good morning, everyone. So we are starting a new session. So today we are going to have a mix of first data centers and second, a new model on transmission and expansion planning. So first for data centers. So I have here my colleague. Oops. I did it the other way. My colleague Deep, who is going to provide an intro. You will present yourself later, right?
Yeah.
Okay, so he will introduce himself. So first talk is going to be about, in general, data centers and energy consumption. Then we will have Javier, who you already know. He will talk or will present some modeling he has done on how to invest for data centers, to provide energy to data centers. We will have our break. Then Andres will present the transmission expansion planning energy systems model, okay, which is OpenTethers, which is an open source model that anyone can use, and he will teach you also how to use it. And finally, Mehdi, who is one of our classmates here, he's part of the managing engineering, engineering manager in the central utilities plant. So he offered very kindly to a visit to the central utilities plant by 2:30. So if anyone is interested in joining us, feel free to go to building E42C. I will send later everything by email, okay, all the details. I've been there, and it's a great opportunity to see like a real installation. Okay, so with that,
Sure.
Can you hear me? I guess so. All right. Well, thanks, Pablo, and welcome to I'm guessing the fourth day of the class. Fourth day or third day? Third day. Third day of the class, yeah. As Pablo mentioned, I'll be talking about this entire area of data center grid interactions and answering questions on how to power data center growth. This is an overview of work that we have recently started at the MIT Energy Initiative. Part of the connections to research work would be with this following collaborators: Shangoshin and Xiaohui Lu, with whom I'm working on flexibility of data centers; Professor Saurav Amin and Rahman, with whom I'm working to understand interconnections of data centers and generation to the grid; and some work on placement and planning for data centers with Rory McDonald, who probably spoke yesterday, right? Okay. Just a show of hands, how many of you have a background in electrical and computer engineering? All right. If you don't mind me asking, can I know what other areas are being covered here? Like what are other fields of expertise?
Reliability.
Nice. How about you?
Oh, I have a math background.
Okay, that's not bad. That's good. How about you, sir? Did you say you are ECE? Behind you.
Oh, systems and product.
Okay, that's all related. Again, this is going to be less mathy than the other talks. I will actually pinpoint certain follow-up presentations, which will kind of, I would say, extend from what I'm going to present. I think Pablo has already mentioned it. We are affiliated with MIT, which is the energy hub of MIT. We do a lot of research. There are a lot of questions with respect to sustainability, affordability, and just general provisioning of power across different infrastructure systems. We do a lot of events, so if you have questions or are interested in energy-related research or work, feel free to contact or come by. We are in E19, which is kind of like on the other side of campus, right near Kendall. At MIT, I'm a research scientist. I also manage the Data Center Power Forum, which is a new initiative we have started to understand this critical question of answering different research problems associated with powering data centers in the grid. And this is in collaboration with a lot of industrial partners, including big tech, energy companies, sensing companies, grid operators, things of that kind. And we are hoping that this engagement will lead us to at least answering or giving a perspective of where MIT thinks these kind of questions can be answered in. I guess the previous 2 days have been morely about generally grid planning and operations, right, Pablo? Okay, and tools. So I'll try to motivate how for this particular problem of answering the question of how do you connect or fuel the AI growth and the data center growth in the power grid, how some of the tools and discussions that happened in the previous days and also which will happen in the future, how they kind of connect, right? The reason we are talking about data centers, and I'm pretty sure there was no data center power grid course happening anywhere 4 years back, is that this is a very recent development. Data centers as of now are 4% of the total energy needs, at least in the US. And depending on who you follow, the expected growth that a lot of people are projecting in the next 5 to 10 years is going to be around 10%. So they'll grow to around 10% of the total energy load in the country, in US. Such kind of forecasts are also there from across the world. To give a measure of where things are, the hope is, or at least the forecast is that in the next 10 years, the amount of load which will come from data centers, the new load which will come from data centers, will be equal to every other new load which is coming in the system. So if you consider a total amount of new load in the system over the next 10 years to be X, 50% of that is just going to be data centers, and 50% is going to be everything else, all other industries, domestic, household, all of that. Okay. Now this is a problem because one, it is a big size, and two, it's a very rapidly growing energy demand. In the US context at least, over the last 2 decades, majority of the demand growth has been pretty stagnant. It has not grown by much. As such, the normal procedures and plans and the ways in which we understand and augment the grid to fuel new load may not be sufficient for this upcoming data center growth. Okay? And there are a lot of, if you have such rapidly increasing load or just a rapidly increasing industry, there are a lot of questions you have to answer. So for example, there are also a shortage of chips to fuel AI workloads and how to build data centers and other things. But what has become a consensus fact right now in US is that the primary constraining factor for data center growth is energy supply. So there is not enough energy or availability in the grid to support data centers. And part of the things I'm going to discuss will be about how you can think of innovative ways in which you can answer that question. All right. Now, talking of data centers, there are different kinds of data centers. At the small level, there are enterprise, small edge data centers. You also have high-performance computing in universities, which is also like a data center. You can have big servers. Depending on the size, you can call it a data center. But the primary two, where majority of the growth is going to happen, are going to be in the larger scheme of things. So these are hyperscale data centers or co-location or multi-tenant data centers. So these are gigantic facilities consuming energy anywhere from 70 to 150 megawatts of power. And it's a lot of concentrated energy requirement in very specific geographical areas, right? So it's not that data centers are growing all across the US. They are only in certain pockets where such kind of growth has happened. And this actually creates more problems. It's one thing to say you want to serve X amount of load in the system. It's another thing to say you will have to serve X amount of load, but they are all located in one particular location or in one particular geographical area. Okay. Now, in terms of load itself, a majority of the load in the data center is actually from IT consumption. Okay? So IT consumption means the energy required for the chips to run the different kind of AI tasks that they run. All right? So for example, for large language models, it can be training and inference. Aside from it, there is also cooling. Now, depending again, I'm giving some ranges because these ranges are all over the, I'd say if you look at literature, they're all over the place. As IT does computing, you consume the power, it produces heat. There's an entire angle of cooling associated with it. So how do you take that heat out? How do you cool the data center? And that itself consumes power. Depending on how efficient it is and depending on the technology associated with cooling, it can go anywhere from 10 to 40%. And aside from it, the AI workload, which is a primary economic driver of data center growth, cooling, there's also this housekeeping energy which is required to run the other things or the power infrastructure which is there in the data center. Tomorrow there'll be a talk by Xiaohui Liu, who's a postdoc working with us, who will talk more about the nature of loads at different time scales of data centers and their particular characteristics and how to harness their flexibility. Now, what is unique about this data center load is, again, if you look at big tech and other new data centers coming up, they are considered to be very economically expensive assets. They do AI training and task. If you believe the hype, AI is going to revolutionize your world. So it's a very economically important thing. As such, when data centers come and want to get connected, they really want very high reliable electricity delivery. So they want a connection which can guarantee that with almost 100% probability, 100% confidence, power is always going to be delivered to a data center. Okay. Now I'll go later into what I mean by reliability, how that is measured in a power grid context. But reliability actually means if to bring in reliability in the system to building redundancy, which means you have to over-engineer a system, and that has additional cost, it takes time, and so on and so forth. The other thing with reliable delivery is, if you want very reliable electric delivery, it kind of produces a challenge to power it using renewables only. So there are all kinds of engineering challenges about answering this question about how do you give reliable power if majority of your fleet actually is renewable or intermittent. So there is a lot of push happening right now to understand what is the right mix to fuel data centers. On the other hand, data centers also have very strong, at least the companies have announced very ambitious net zero emission standards and emission goals. So they want to operate it in a clean way. So there is this contrast, and there was a statement about you want reliable power, often firm power, and on the other hand, you want to have clean power and to serve your data centers as well. And how do you answer those questions is important. And as I mentioned, the fact that it's geographically clustered and the growth is very rapid, that has additional problems to it also. Okay. Now, as part of this class, this was a lot about grid planning and grid studies. Data centers, if you believe me, the way it is going to operate is they are going to have to connect to the energy grid in some shape or form, all right? Now, if a large load is part of the energy grid, this is my depiction of what the energy grid looks like. There's generation, transmission, it steps down, is kind of like the sub-transmission or distribution, and data center is one of those loads which will connect to the grid. If you want to have a large load connecting to a data center, you have to ensure that the overall grid itself has to operate securely, safely, reliably at all time scales, all right? And the reason I mention all possible time scales is if you look at generally how the power grid or energy grid operates, it actually goes all the way from decades and years of years, all the way you can go to microseconds. And there are all different kinds of operations that happen in a data center, in a grid at that level. So on a very slow time scale, you have transmission distribution planning. This is kind of some of the tools that were talked about yesterday and also maybe today, about where do you build things, where do you plan things, where do you site things. If you go at a slightly faster time scale, which is in hours or minutes, you will come to what would be known as scheduling and markets and things of that kind. So this is mostly dispatch decisions for generators. If you have flexible workloads, how do you move them around in space and time? That will happen in minutes and hours. And we'll also talk a bit about this tomorrow. Finally, if you go even in faster time scales, let's say seconds and below a second, you'd come in the regime of what would be called as stability and dynamics in power grids. So on some level, where you look at the slower time scale, you can the power grid can be looked at as a network flow problem where you decide and solve power flows. Whereas if you go at very shorter time scale, you have to look at it as a dynamical system. So something will change, it will lead to frequency changes somewhere else, that will lead to other dynamics happening in the system. This is the regime where control happens. This is the regime where protection happens, faults and failures in the grid. When lines open, how does the automatic control reacts back in the grid? This is the regime where it works. And data centers also impact that. And I'll briefly mention why that has also become important. All right. And again, just to push back on the fact that size matters a lot here. So if it was small loads, you would not worry about all of it. But if it's a large load, like a data center, and also a large load which is moving a lot, so there's fluctuations happening in a data center, you have to think about transmission distribution planning. You have to understand markets and flexibility. You also have to understand how stability and protection matters. Okay. And this entire picture where you have to go all the way from slower to faster time scales, it creates complications in analysis, it creates complications in the kind of investment you have to do in the grid as well. Okay. So that was my brief introduction of what data center loads are and why this is important. What I'll be going now is talk about 3 different areas which will also relate to follow-up talks which will happen today and tomorrow. Which relate to data center grid analysis. One of them is going to be about data center planning and siting, and about grid planning particularly, with data centers in mind. The second is going to be about resource adequacy and flexibility. All right. So resource adequacy means there's sufficient amount of generation in the system to support the load even during periods where the total load is at its maximum peak. Okay. So that's a slightly slower time scale compared to, let's say, planning. And then finally, I'll talk briefly about protection and stability, and at least certain studies that have happened about the kind of problems that it creates. After that, I will talk about, because this is an emerging question, there are different parts of at least the energy ecosystem who are trying to answer and facilitate conversation in it. I'll talk about recent changes in some regulatory authorities happening in US, as well as in some independent system operators, the power grid, I would say, operators in the US, about how they're trying to answer it. And then link to certain research work which I'm involved with to answer some of it. All right? And we have I think around 35 minutes. So if you have questions, feel free to raise your hands. If you have comments, if you do not agree, that's fine as well. So we can have a discussion throughout. As I mentioned, this will be slightly less mathematical. Okay. Now, the kind of questions that at least at MIT we are trying to answer is one is in this grid map, you are starting off at generators, right? So if you have new loads coming in, on some level you have to provide and support those loads, so you might need new generation. So what is the right kind of generation that would be essential to provide power to the grid, making sure it is able to be reliable, making sure it can offer clean services also. Okay. Secondly, generation is just one piece, as everything is connected to a interconnected grid where one part of the grid can affect something else. You have to also understand grid analysis. Right? And grid analysis would mean answering questions about can the grid operate reliably when there are weather events. This is what I think was covered a bit in planning. When infrastructure is aging, things are getting decommissioned, how do you do things of that kind? There are also other questions with respect to cybersecurity, demands, services, and all of that. Another area which is worth analyzing is the data center itself is not a static load. There is a lot of controls, there's a lot of resources and redundancy built inside a data center. So one can also think about research about how you can efficiently use the data center itself to provide services back to the grid, or at least at the very least, minimize the adverse impacts it can offer into a grid, all right? So this is like saying questions as, if there's a lot of fluctuations in the grid, in a data center, which can lead to frequency events in the rest of the grid, can you understand the design of AI training itself or the kind of resources you can build at the data center so as to reduce those big fluctuations on site? Finally, and this I don't know if you're covering this at all in this talk, and this is not my focus area, but aside from just the grid and the energy and the data center, there's all this other affiliated infrastructure which are part of the ecosystem. So one of that is carbon capture, let's say. The other is, as I mentioned, cooling is a big problem in data centers, which means there is heat produced. Can you use the heat efficiently to provide other services to neighboring communities and things of that kind? Finally, data centers also use a lot of water. In fact, one of the major pain points for data center growth across the world, including in Southeast Asia, where I'm from, has been this use of water. So they consume a lot of water, primarily for cooling. And a lot of areas actually have water stress because of agriculture and other industries and just the population which is there. And there is a lot of pushback on if data centers can run with reduced water consumption so it does not adversely affect the neighboring areas. Okay. Finally, and this is related to at least one of the speakers will speak tomorrow. He's from the Center for Energy Policy Research, CEPR. There is a lot of work happening in energy policy. So I talked about engineering problems, about grid connections, data center itself. All to answer those questions, what might be necessary is you might have to rethink energy policy because you'd require money to build things, to provide things, and eventually all of this money gets routed back and gets paid by the end users or customers. So there are questions with respect to tariffs, cost allocation, just general energy policy related to facilitating a sustainable, affordable energy transition, which can also support data centers. So this is a picture of, let's say, the kind of rulings that will come up. And it is happening very fast right now, at least in the US, about trying to answer or change the rules to answer some of these questions about facilitating data center growth. Okay. So this connects to the next thing which I wanted to talk about, which is particularly when I talked about a grid interconnection or large loads connecting to the grid. It is not basically just a question of connecting and just making sure there is energy supply to support that load. There are different kinds of questions, and these are often questions which are very well regulated in energy sector that have to be answered or thought about before connecting a large load. So one is resource adequacy that I briefly talked about. So resource adequacy is basically the thing which measures if there is sufficient generation and transmission resources in the system to provide power during high loading events. So for an average day, let's say in March, where the load is normal, temperatures are okay, the grid might be sufficient and there might be sufficient amount of capacity and generation to support. But when you plan and decide on the right grid design, you have to make sure that there's sufficient amount of capability to provide power even during a bad day in July when temperatures are very high and everyone is trying to consume the high amount of power. In areas such as New England, it can also be, let's say, on a cooling day, on a very bad winter day where temperatures are very low, there should still be sufficient amount of resources in the grid to provide power. The second thing which I'll talk about is reliability. Okay, so reliability is basically the measure or metric which tries to say that the lights are on 24/7, which means there can be random changes happening in the grid. A transmission line can go off. I can switch on a particular building. I can switch off a particular building, which means a lot of the loads and generation and other equipment in the grid can be stochastic or can fluctuate. Reliability ensures that even though those things can happen, the overall grid does not destabilize and fall apart. Okay, so that everything still operates smoothly and you don't notice it and there is no disruption happening in the system. Finally, related to all of it, there are questions about electricity market. I think you covered something on markets, right? Yeah. So if you have large loads and these things coming in the market, energy prices might get impacted. A lot of those markets are, not just short-term markets, but long-term markets. There are questions about signing PPAs. There are other aspects of the market like capacity markets, which is kind of paying for resources so that they can provide power during, resource adequacy events. All of those markets might get impacted if you bring in a lot of load in the system or a new generation in the system, and these have to be thought about. In US at least, there are two agencies. So this is the FERC, which is Federal, I think it is Electricity or Energy Regulatory Commission, sorry, I should know that. So FERC is the governing body which does a lot of this. I'd say the governing body which regulates both the energy and a lot of the gas network in the country. And for a lot of those studies on reliability, because the energy grid is not necessarily just in US, it's connected to Mexico in certain places and a lot in Canada. There's another authority called NERC, which is North American Electric Reliability Corporation, which studies these reliability questions and understands what the impact on the grid can be. So the question might be, you have a large load connected to the grid. What if I disconnect a large load? If the breaker fails or a transmission line fails, what happens to the rest of the grid? Will it sustain that, or will it be able to ride through that particular fault, or will it not? Things of that kind. From someone in electrical engineering, when you talk of reliability, which is often the shorter time scale, there are also mathematically precise ways in which we can understand how the grid operates. So there are, and I will not go into details of it, there are questions of small signal stability, which is about small fluctuations. There's transient stability. There are power quality, harmonics. As you have probably already noticed in the past 3 days, the way the grid operates is, it is actually a AC or alternating current waveform. So at shorter time scale, you cannot ignore the fact that it's actually a wave. It's not a steady electricity signal which is going on. And this wave will have all these things, harmonics, fluctuations, flickers. There's a frequency of that particular wave, and things have to be within, I would say, a stabilizing, controllable paradigm so that the grid can operate normally. Okay, so these things are there. Okay. Now I'll come into some of the questions that, the research questions and the kind of questions which would be interesting in this particular area, including which will lead to, I think, discussions in follow-up talks. So one question which comes up often is, siting decisions for data centers. So you have large data centers coming in, where do you connect? So this relates a bit to, I think, capacity expansion, other models which are talked about or also be taught about. But generally, when I think of capacity expansion, I think about a system level study where you are looking for overall load growth in the system and you decide on where to build transmission lines, where to build generators. Siting decisions often is more localized in the sense that you know that a generator or a load is trying to connect at this particular location in the grid. And then you have to answer the question about what other things have to be changed in the grid and who has to pay for it so that that generator or that load can connect securely to the system. So it cannot happen that you bring a nuclear power plant and you say, all right, outside of Boston, I'll just connect it. The grid may not be able to sustain that kind of the voltage it wants or the amount of power it is trying to inject. So there is a grid study similar to capacity expansion done every time a new generator or load tries to connect to the grid, and these are what siting decisions are. Now, as would happen for data centers, because so much investment is required, what often ends up happening is that there are new configurations that are being thought about. So some of the configurations that people have thought about is that, okay, if it takes me forever to connect to the grid, maybe a data center and a generator can connect to the grid together. Now, these configurations, to enable it or to accept the proposal for a connection of that kind, it has to be analyzed and studied. The problem is, at least in the US context, this new kind of configurations with large data centers and large generators connecting the grid together had not been modeled or studied previously in greater detail. So to okay a connection of that kind, there is more analysis needed, and this is still a research and open question, right, in literature and also in the industry itself. The other thing is when a large generator connects or a large load connects to the grid, they have to pay money because often transmission lines have to be built to provide power to it. And then it is not a straightforward allocation strategy. You don't just build a transmission line and you say, all right, the new load is paying for everything. They would do more study to understand this transmission line, even though I'm building for this new load, who is it serving? Is it serving someone else also a little bit better? So and then that decides on, and that leads to a question about how do you allocate the costs associated with this new investment that is happening in the grid. And when you have different modified configurations of generator and a load connecting together, which means they will not use the grid often, only once in a while, there are questions on how this cost allocation and transmission charges are decided. So that's a slower timescale thing, right? You have a generator or a load trying to connect to a grid. Where do you place it? How do you allocate costs to it? And I think one of your talks is going to answer part of it in the sense of how do you site and size. The second thing, which will relate to a talk which Xiao will give tomorrow, would be to understand or manage or harness fluctuations from data center. So this is at a faster time scale, often in minutes to hours, and also actually at faster time scales than that. So this is basically a timeline of how the power consumption of an AI data center would look like when it is doing AI training. So one might think that when a data center is running, it has a steady load profile. What actually ends up happening is just by the nature of in which AI training happens, there's a lot of fluctuations that happen. So these initial fluctuations that you see here are mostly just computations happening on chips. A lot of AI training is distributed. So the way the paradigm works is they do these computations, then everyone stops, they exchange information, something known as checkpointing, and they again start computing again. The minute they do a checkpointing, because those large computations are not happening, but they are just exchanging information, you see that power immediately drops. And it drops often by a pretty significant margin. A large enough margin, which means that the grid will see a power drop happening at that particular site. And because it's a dynamical system, there are AC waveforms. A large change in load can lead to the frequency in the grid itself being changed, right? And this is probably, I think, in your afternoon when you do a trip of the system center, you'll probably look at, I think, monitoring systems where you're looking at the frequency or the voltage of the system, right? So AI training, just the general way in which it happens, it can lead to changes in frequency and voltage, and they have to be arrested and understood. Okay.
Like this,
Yeah.
is this just basically put on onto the grid, right? That stress and the variability, or does that get taken up by the batteries, or is like UPS, the battery backup unit, or kind of a ESS that they have outside?
That is a good research question. So one of the questions that we're trying to answer, and others are also trying to answer, is can you not arrest it directly there using a storage device? Now, I don't know if it came up in the classes before, is that the way the power grid generally operates is you would only do things if you're required to do it. So let's say there is no rule right now saying you should arrest it at site. You cannot tell a data center that, hey, you should do it. Because then they can come back and say, every load who is doing any kind of small fluctuations, they should arrest it on their side as well. And we don't have a rule like that. So generally what ends up happening is if you have this kind of fluctuations, there is another market outside of energy market called ancillary services market. This is when the power grid operator purchases fast-moving responsive resources. This can be fast-moving storage. It can be just generators which can respond to commands every 4 seconds to move their generation very fast. And these ancillary services are particularly purchased or procured so that there's sufficient amount of, I would say, leeway or backup in the system that can arrest this on a system-wide level. Now, what would happen is if you have these kind of fluctuations happening a lot, on one level what is going to happen is you would need to buy more ancillary services. And eventually when you buy more ancillary services, who pays for it? It goes to your bill, all right? So So those are questions. So now for a particular kind of large load, maybe a solution is that you should arrest it on site. What you offered is a power-based solution. So you can have a storage which is very well synchronized and it basically moves in the opposite direction to arrest it. There are also startups right now who are proposing something else. They're saying that we will have one more small computing happening, some matrix multiplications, crypto, you can take your favorite choice. That would be tuned exactly to it. So the minute the power falls down, that will start. It will do some matrix computations, the power will go up so that you produce a flat profile. Now, if that is viable idea or not, that's open for discussion, but there are startups trying to do it. Yeah. Yeah.
What are the units of that consumption? Because I cannot see very well.
So these actually on a data center level, it can go all the way from 5 to 30 megawatts.
30 megawatts?
Yeah, 30 megawatts. So
Is data 8,000?
no, this is actually watts. So that would be 8 megawatt, 8 to 5. So this is a 3 megawatt jump. Yeah, this actually says watts. So, and this is just one particular a set of nodes on one particular very, I would say, synchronized operation. There can be in a large data center, it can be a lot more. There are a lot of tasks happening at the same time. So the jumps can be more. In fact, yeah. So this is one from Google. So this is their data set on the kind of fluctuations they can see. So you can see like 10 megawatts happening. Now, one positive from the grid side actually is that these kind of fluctuations are not just detrimental to the grid, they're actually also bad for the data center itself because the chips to see that kind of power surges can damage equipment. So there is research happening even on, I would say, the computing and architecture side to understand how do you mitigate it at source by changing the way the data center internal computations themselves happen. Okay. Going to even faster timescales, there is this entire area of data center protection. And it's not my exact research area, so I will not go into much detail of it. But this basically relates to the fact that all resources in the grid have protection built in. And just like the word protection, it is basically saying you have kind of like a controller. If you see that the external to your system, the rest of the grid is operating in a weird way, or the voltage and the frequencies are going haywire, to protect yourself, you will just disconnect from the system. Okay, so that is what protection does. Often, if you believe data center operators, because their equipment is so expensive and the kind of tasks that they do is very crucial, and they have sufficient amount of backups already built in at the data center, what often ends up happening is that protection is over-engineered. So if they see a voltage fluctuation or a voltage event happening in a grid, they will disconnect. Now, if a household disconnects, that's still fine. But if you have, let's say, 5 data centers, each consuming 100 megawatt, disconnect at the same time, the total amount of energy imbalance in the system can be pretty gigantic, and that can lead to, again, follow-up problems to the grid. So for example, this is a real timeline of that I took from the Eastern Interconnect. So this is one big part of the US. There was a transmission line fault which led to some voltage signatures, weird voltage signatures. Not that bad because the rest of the grid and the rest of the loads stayed connected. But data centers, because they're over-engineered in their protection, they saw 3 of those pings of voltages, and what they did is they disconnected. And this is the overall system load in the system. In the entire Eastern Interconnect, this is not a city or something. This is almost, let's say, 30% of the US. It's a gigantic part. You can see there's 1,500 megawatt of power of load drop. Now, on a faster time scale, the way the grid operates is the total amount of load in the system and the total amount of generation in the system have to be constant. This balance has to be finely maintained so that the frequency of the system, everything runs on 60 megahertz, 60 hertz frequency. This balance is needed to make sure that that frequency stays constant. All of a sudden, if a 1,500 megawatt drop, what has to happen is the generation also has to come down by 1,500 megawatt so that there is not more generation in the system than load. If that happens, the frequency can grow up, and if that is not arrested, all of a sudden you can have transmission lines and other breakers moving off, getting off, and eventually the grid is going to disintegrate. This is what generally happens when people talk about blackouts. And we also have people from Spain who probably experience it firsthand. Like eventually there's disturbances, there's instability in all of it. But in the final few seconds or milliseconds, what ends up happening is one of the state variables, which is frequency or voltages, can go haywire. Automatic breakers are going to open throughout the system, and then the grid is going to collapse. And then there's a lot of money involved and there's also a lot of engineering effort involved in connecting the grid and turning it back altogether. Okay. So protection is another major issue, and there are ways of answering it. Now, I answered 3 questions, right? So didn't answer 3 questions. I mentioned 3 things. One is this planning problem about where do you site it. The second is this fluctuations and resource adequacy and things of that kind. And finally, there's protection. Now, these are not questions which just came to me. What actually ends up happening is if you have a new generator, this picture is actually for a generator, or a new load trying to connect to the system, all of these things have to be carefully studied, analyzed, potential solutions figured out. Only then a connection is enabled in the system. This is what is known as an interconnection queue. So every time you want to connect a gigantic generator or load to the system, you have to go to either a utility or often to the overall system operator itself. You have to propose a plan of the generator or the load, the total amount of megawatts you have, how much you can move, where you want to connect, what voltages you want to operate on. And then this transmission system, the independent system operator or the utility will have to study the different timescale impacts of that large load or the generator on the system, propose potential solutions if enhancements are required, and then ask you to pay for it, and only then you can get a connection. This entire process takes a long time. So there is this entire thing which is known as interconnection delay happening, at least in the US power grid. There are a few reasons for it. One of it is the fact that generators and turbines take a long time to procure and make. Because we have not seen a lot of load growth in the past 2 decades, we don't have sufficient amount of generation, or I'm not even calling it generation, manufacturing happening for turbines across the world. So if you ask GE or Siemens, they would say that our turbine orders have been backdated for 5 more years, so they cannot take any new orders, right? So there's that supply chain bottleneck there. There's regulatory delay, just because you have to study all of it. And then there is other kinds of delays happening in the system as well with respect to policy changes about where you can procure things for, where you can't, all of that, right? This is a pretty bad problem. The reason is data centers themselves is a very fast-moving industry. If you say you can connect in 6 to 7 years, you might have to rethink your entire economics of it, because the design of chips and the kind of market for AI might change in 6 or 7 years. Secondly, it's a bad thing for the grid itself, because if you have a load which may or may not join and you're doing capital investments, it leads to both financial engineering issues, because eventually if the load does not emerge, it does not connect, you have already procured and built a lot of things on the grid. Now, who has to pay for this new things that you built, but there is no load to consume it? It has to go to the existing load in the system, or you have to declare bankruptcy or things of that kind, all right? So there are those questions there as well, which comes with having delays in the system, and we are trying to answer some of them. Do you have a question? No? Okay. And again, these are things which they are not just coming to me, they have been discussed right now for quite some time, so including in federal and regulatory authorities. So I'll just briefly mention 2 things that have happened. If you followed what Rodi talked about or Pablo talked about, or even today when you would hear about capacity expansion or transmission expansion, you normally build a grid to satisfy a future scenario, different kinds of generation and load happening in the system. Often this kind of analysis looks at peak loads or average loads, all right? So what has ended up happening is the consensus has come that such kind of, I would say, coarser models of resource adequacy may not be sufficient to answer the question about getting data centers connected to the grid faster. So in particular, what people are trying to understand is that instead of just saying that there is not sufficient resources in the system to support the load, we should answer more fine-grained questions about there is not sufficient generation in the system to support the load for key periods of time, all right? This is because when you talk about peak load and loading in the system itself, it is not a constant thing. There are periods where the load is low, there are periods when the load is high. Now, if I say I don't have sufficient generation to support the load, it's a very different thing if I say I don't have sufficient generation to support the load for 1 whole month, versus if I say I don't have sufficient generation to support the load for 2 hours every year. This temporal component is important because this temporal component can lead to differentiated solutions. So for example, if I say I need more energy for 1 whole month, I have to build a generator. But if I say I need more energy to just support the load for 2 hours, I can use storage, I can use some kind of flexibility, I can ask certain loads to get their power low, I can offer this kind of differentiated solutions that can come in. All right? So there is clearly an understanding that there need to be robust reform, and this will be required to make sure that the AI gets connected. So 2 things that the Department of Energy has proposed is changing this metric by which you look at reliability in the system, reliability in the system, to also look at not just outages or basically insufficiency in the system, but also how much is the differentiated difference between the total generation and the load in the system, but also what is the duration for which you will get outage if you do not build new generation. Okay, and the reason why it's still slightly further off. So what would happen is if this kind of metrics are accepted, these metrics will now go in as constraint inside your planning or resource adequacy studies, and this will give to differentiated answers for your maybe solutions to where transmission should be built, where generation should be built, what kind of generation can be built, and things of that kind. Yeah.
Meaning that today there is no presence in the law or in the regulation on how these laws should connect for the power quality that should be related to this type of laws, because normally that's something that you would find in regulation. Is there something about it yet, or do you see that coming on?
So there are questions being thought about right now. So generally, the load model itself was not that well modeled to look at system-wide planning for the grid. Generally, it is generators which are very well modeled. But if your loads are very big, those things they're getting discussed, at least in Texas and a few other places, that loads has to be explicitly modeled so that those studies can be done properly.
Currently, there is no requirement for this type of loads to be modeled and how they are going to.
To the best of my knowledge, no. There is some coarser models which are provided, but the finer detailed models, they are required at the utility level. So a small utility will have to look at it, but on a grid level, they don't model the load exactly in the system. They model the peak load, average load, and things of that kind, but finer timescales are less modeled. And when they build a grid, when they do transmission expansion and all of that, they look at loss of load probability and all of those things. So they try to see, and there are some concepts about you should be building the grid so that the bad event can happen once in 10 years. Okay, you have to build the grid to prevent the once in 10-year event. This is basically, if you look at it mathematically, it comes as a fact as saying you should build a grid so that the total generation, total load should be equal on some level. Now, what I'm saying now is that there is thought about making those statements or requirements slightly more, I would say, more integrate. So you have to bring in time, you have to bring in how long there is this imbalance in the system, what is the magnitude of the imbalance, so that you can get more, I would say, realistic solutions instead of over-engineered systems. Okay. All right. So and they have also done studies to see that under these new metrics, what kind of problems can happen in the grid when you don't build new generation, which can then guide different ISOs in building the right generation for the right kind of metrics that they care about. Okay. Secondly, as I mentioned, why this kind of metrics about time is important. There is a lot of work to show that generally the load in the system itself is quite flexible. Not just flexible, sorry, it is not constant, it changes a lot. The total amount of time in the year for which you get the peak load is very, very low. So it's again a few days or a couple of days or maybe a week. So you should, if you're deciding on planning the grid, you should be aware that I am trying to do a lot of build up for that 1 week. So maybe my solutions and the cost associated with the solutions should be conducive for it, right? So I'll just give a small example which is outside of data centers, okay? There's a lot of electrified heating happening in the system right now, okay? So a lot of our building heating happens by gas. There's a lot of move gas-based heating to electrified heating. Now, if you do electrified heating, what is going to happen is in winter, the amount of electricity that you're going to consume is going to grow, right? As a system, it is going to grow. Now, you have built generation in the system to support some amount of load in winter. If most of the heating goes from gas heating to electric heating, what can end up happening is eventually for those very bad days in winter where the temperature is very low, like the last week and all that, the total amount of electrified load from heating can be so high that you might have generation inadequacy in the system. What that would entail is that the utility has to either procure new generation or has to pay this kind of more expensive generation to come online so that they can support that load. Now, if this was an event which is happening throughout the year, you should always do it because everyone's electricity rates are going to go up, they will get supported. If it is happening for 4 days of a year, and you have to pay this generation to come online. Yeah, there's additional payments to be made. The generator has to be ready so that it can come online. It kind of begs the question about that. Is that the right solution for it? We try to electrify heating, we try to be clean, but then we are making sure the grid is having a lot of problems for 4 days. Is bringing a new, more often dirtier generation online for those 4 days, is that the right solution, or there are other solutions associated with it? Okay, so this temporal thing is often important. The fact that peaking happens only infrequently. And just generally, there's been changes. There's a lot of federal changes which has happened. So this is the yellow curve is generally how loads and loads connect or generators connect to the grid. This is known as interconnection agreement. It'll be hard to read what I've written, but generally what happens is normally when a load or a generator comes in, at least this is the paradigm in most of the US, the grid has to facilitate the sufficient transmission to serve the load at the peak load level that the load has. On the other hand, now because people recognize there's not sufficient transmission in the system, they're coming up with alternate agreements. They are now saying, all right, maybe a generator and a large load will come in together. The load will take majority of the power from the generator, which is 900. It will only take 100 megawatts from the grid. So the grid is responsible for building transmission just to support 100 megawatts. Now it can very well happen in a good day, there is not a load in the system. The large load can be able to take more power from the grid operator, but the grid operator will not guarantee that anytime you ask for more than 100 megawatts, the grid is going to give it. So it has to buy it from the particular generator and its responsible site itself. So this feel very simple because there is financial instruments behind it and studies behind it, making sure that this kind of flexible agreements can actually be actionalized and can be operated is not a trivial thing. And it also has to pass through a lot of regulations and things of that kind. Okay? So instead of steady connections, there are all kinds of questions now on building flexible connections or different configurations. This is a very different configuration where it says we are going to build you 1,000 megawatt eventually, but for the time being you are going to use the generator, and you will only get this eventually when this gets built. So you can connect already instead of waiting for a longer period of time. But there are open questions still. I know how to allocate money when I connect a large load and try to build the entire transmission line or transmission asset to provide 1,000 megawatt. I do not know what it means to allocate money for building this, about who pays for it, when this 100 megawatt or versus when this 100 megawatt today, but eventually it is going to be 1,000 megawatt. In the intermediate period of time, how do I allocate money? Who pays for it? Yeah.
For all these different types of issues where just say you have low growth, right,
Yeah.
proceeding when you have that capacity on that,
Yeah.
It's kind of like a whack-a-mole, right? It kind of shifts from place to place. But how big is this, like in aggregate? Is there any kind of estimate for the
Total?
Yeah, correct. Yeah.
I have to take a look. I think it is 50 gigawatt for the next 10 years for data centers. I can just follow up and I think it's 50 gigawatt from data centers and 50 gigawatt of other loads which are coming in.
Okay, so like 100 gigawatts of additional.
Yes, yeah. But the problem is, this 50 gigawatt, they would try to, at least if you go by the contracts that they're signing, they would want it in 2 months, if possible. So they want to build it immediately, if possible, right? So that is the problem. If they said we want 50 gigawatt in 10 years, I have a lot of time to study it and do it properly. And not just that, the companies who are building it also have money. So they, like previously, you would not have a steel plant coming in and say, I will buy a nuclear reactor and connect together. That configuration did not exist, just financially did not exist previously. Now, those I would say offers are coming in, and hence the grid operator has to respond and try to see what changes can happen. But in a way, it is also nice that a lot of the way we looked at or analyzed the grid was very historic. But now there's a way to, rethinking always leads to better solutions, in my opinion. Okay. And finally, just very briefly, I don't have time also because people are going to talk about it. We are looking at some of those questions. So one of the questions that we are trying to answer, which is similar to what your talk is going to be on, is if you understand that you cannot get all your power from the grid, so you cannot be in this configuration, but you have to be in a configuration like this. And also knowing that to build resources, it takes time. How does a data center basically understand sizing of resources co-located with it to get as much power as it wanted? So this is like saying you want 100 megawatt, the grid can give you 50 megawatt, and during those high peak winter days or summer days, you can only get 40 megawatt. should the data center invest in storage? Should it invest in a gas connection? Should it invest in some backup diesel fleet? How can you utilize them efficiently? How do you understand where to put the money in and where should you connect so that you can get the amount of power that is required and as fast as possible under the constraints of the system? Okay. And so, for example, so you have large loads, you have on-site resources. How do you, size them to make sure that you can get the power that you wanted while accounting for the opportunity cost of a slower connection? So this is specifically targeted toward data centers because at least they profess that getting a delayed connection of 5 years is a very big economic detriment to them. So if you do not want to lose out on power, what is the right solution that you have? We've done some initial work, and we've kind of seen that if you have this cost of delayed connection coming in, you obviously will get different solutions. So if you're a particular load whose opportunity cost is less, you don't really care about if you get connected today or in 5 years, the solution would be build a transmission line. But if the transmission line is going to be expensive and will have delays associated with it, and you want power tomorrow, it really should give you different solutions. Okay. Secondly, there's another angle of how do you use the flexibility inherently built at the data center itself. This will be talked about tomorrow by Xiaovi. So we are trying to understand if there is a data center with a storage device which is flexible, the workloads themselves are flexible, how can it be combined together? How can you do co-optimization of both of it? We'll go to the math of it. So that you can not just satisfy your own quality of service, that is you can solve your AI workloads as per the deadlines, but also offer certain kind of services back to the grid. So you can provide some reserves, you can provide some flexible ramping products back to the grid. This kind of services might become necessary because as is already happening is if you connect large loads in the system and these large loads have gigantic fluctuations, the grid operator can very well say that you can get connected, but up to a particular peak load limit and also with a constraint on the kind of ramping your load can have. So it can say you'll get 50 megawatt, but make sure that if within 5 to 10 minutes, you never go beyond plus minus 5 megawatt. Okay? And some of the services and this storage can be used for providing that. Finally, this entire problem of interconnection is actually very interesting. It's one of those problems which interfaces across policy, engineering, different timescales, and it's a hard problem. It also needs solutions which differ from area to area. The protocols in Texas are very different from in PJM to California. They have different ways in which they model reliability. There are different ways in which they do cost allocation. So one way when we are looking at this problem of this entire process of interconnection of different studies and engagement, we are hoping Gen AI can help us in some of it. Because a lot of tasks associated in solving this interconnection problem is you have to go through protocols, you have to identify the right way in which they're modeling constraints, costs, and then you have to find the right optimization problem, encode it all together, and then solve it. One thing that we're trying to see is if you can use generative AI, feed it the right kind of documents from different ISOs, ask it to curate the right set of constraints, and then construct tunable optimization problems which can solve this interconnection problem faster. It's not going to be faster in the sense that it will just have less human intervention at every step. My final comments in this particular thing would be that we are not trying to come up with new optimization problems. So technically, if someone who's great as Pablo is or Rory is, they can probably write it down very fast. But if you're a data center developer and not a power systems engineer, and you have multiple kinds of documents which are there, this can help you get started in understanding the costs associated with it. Yes?
You mentioned previously that a lot of these data centers are being constructed in similar, or like in the same clusters.
Yeah.
What is sort of the, I guess, key goal for these interconnection studies if you already sort of know where you want to place these data centers already, at least in the US?
So when I say they are getting localized, it means a lot of data centers come in one particular area, and then in another area, a lot of data centers will come in together. It's not a distributed spread across the entire country. Now, what will end up happening is the rules, at least from ISO to ISO, can change. All right. So, for example, California would be different from Texas, from PJM. The other thing is certain data centers also connect via utility. So it doesn't directly connect to the ISO, it will connect by utility, and the utility might have its own rules about how they decide things. There are also rules about different states. The states might have different standards that they follow about load connection, or they have to be ensured as well. So for example, if a data center wants to build storage, there might be rules in the state about how much storage can be built and what needs to be followed. So those things are there. And the other question, which is actually, it reminded me because I didn't comment on it, multiple things are trying to connect together, right? So the study is complicated in the sense that you're studying for one set of connections, then a new load comes to connect. This study has to be aware that there have been decisions taken here, and they're both getting built. At some level, a data center can say, you know what, it's too expensive, I'm not going to connect. So they will withdraw. That decision has to feed into this study that, hey, that line that we wanted to build is not going to get built. So rethink your entire strategy again. So it is complicated in that sense. But I think in my opinion, it's not a mathematically hard problem. It's just procedural delays, and this is where Gen AI can help in speeding up at least some of those things. Okay, I think I'm right on time. So my concluding remarks are, you have a question? Yeah, go ahead.
I'm curious about how is going the ongoing debate about how data centers, if they are connected in front of the mirror in the grid, are they going to purchase the electricity as utilities, generators, consumers?
So if they can connect as a utility or not, I'm not sure, because that's actually at least outside of my I would say knowledge base. But there are right questions in understanding. There's one thing about paying for electricity itself, which is an easier problem. You're producing this much amount of power, you get the cost. But paying for the equipment, which is transmission, paying for capacity, these are harder questions. Because technically your electricity rate also has terms which says, this is the amount, there is a standard thing of capacity market. So you're paying that amount of money every day, because on the day when you need it, the generator is going to be online. Even though it is not providing power right now, it will provide power on the day when the grid is not having sufficient amount of generation in the system. Secondly, you're building transmission. This is capital investment. Transmission, often because the grid is connected, everyone shares it. I cannot say that a line going from Boston to Cambridge, it's only providing power to my house, it's providing power to a lot of houses. A lot of those costs are hence distributed across customers in a particular geographical footprint. It all gets complicated when you make it flexible. So if I am saying I draw 99% of my power from my local generator, 1% from my grid, but that 1% is on the day when I really need it, how do I decide on the capital cost allocation for different resources built in the system? And also, at least the way regulators are, when a particular ISO offers a particular cost structure, it has to get approved. There are axioms on what is fair, what is the right cost. They have to show that this is indeed true before they can build it. This is also related to capacity expansion and other kind of problems. When you decide to build something, you have to offer a plan to the regulator. You also have to show them that these are the alternate options and this is cheaper and better because of blah, blah, blah. And they have to approve it. So it's the same goes with cost allocation. So it's not settled yet. In fact, I think the current policy is that FERC has said this configuration looks good if you can connect, disconnect efficiently. But they have also told them that find pathways in which you can decide on how do you pay their fair share. So this fairness has become important. And that is, so we'll hear in a month, and then there'll be more discussions of it. All right, so that was more or less it. There is a lot of work to be done in modeling. There's a lot of new configurations coming in. There's a lot of studies to do in how do you do planning operations better. We'll hear about some of them today and tomorrow. But if you have more questions, suggestions, feel free to show up at MIT EI, and we'll happy to engage. Thank you. Yeah.
I just had a question on the slide with the 4 different layouts.
Yeah.
I'm just thinking about, Microsoft has 3 Mile Island that they're
Yeah.
reopening.
This
Do
is-
you know, practically which of those, how it would fit into this, something like this?
Okay, so when they initially, the reason why this all came up is they wanted this, or actually they didn't even want this. They wanted 0 here, but they wanted a wire to be connected. And if I am right, what they were saying is that we should not pay transmission. Rates, because every load also has to pay for transmission buildup. And for using the transmission itself, they said because we are drawing our power from here, we should not use it. Now then I can come back and say, and this is what someone said, well, if you don't use it and you don't pay for it, just disconnect it. Or you don't want that also. You want the wire to be there. So they will have to, I think they're okay with paying, to be honest. But then now what is good is FERC has said those connections are now okay, provided the protection is fine, meaning that because it's a nuclear power plant, there are additional questions. You cannot disconnect a nuclear power plant from the grid in US. And so you have to make sure that if the grid fails, the nuclear is still connected, but the power is brought down. Or if the generator connection fails, the grid also has to immediately disconnect so that this connection does not draw power. But the cost part of it, they're going to study now. So, in fact, this entire thing came out because of cost. It did not come out, I mean, it came out because of engineering, but a major part was that, I don't know if it was Microsoft or PG, it might be Amazon, in fact, not Microsoft. I'm sorry. It might be Amazon. Amazon has also a similar connection with a data center, with a nuclear thing, and they wanted to not pay transmission rates. And some utilities raised issue with FERC saying, if you don't pay, who pays? Our customers pay, the normal customers, and then that got into this picture of understanding co-location. And I'm pretty sure in a month they have to reply back about what is the right cost structure they will offer for different connections. Yeah. The one thing that we didn't think about also is that I'm actually done, so you can set up and I can keep talking. Is that it crosses multiple states, so multiple states have different cost allocations and all of it, and then the ISO covers multiple states, right? So there is that angle to it also. That it just because things can long-range impacts can exist, you can have generation and data centers being built in Virginia, and payment being happening in rates going up in Pennsylvania because the line is built there and things of that kind. So